Welcome everyone to chapter 2. In this chapter, right, this is called derivatives. And the claim is that back in chapter 1, we started off on a good foot, right? In section number 4, we were very interested in slopes and rates of change. And we talked a lot about average rate of change and average velocity and things like this. But then we got interested, right? The claim was we didn't have enough information to talk about instantaneous rates of change, right? How is something changing at a particular instant? We needed more information about limits. And so in chapter 1, we took this huge detour about limits, trying to figure out, okay, more precisely, how can we talk about when 2 points are very, very close to one another, right? And this is the idea behind limits. Now it is officially time to kind of get back on track with this idea of slope, right? How are quantities changing? And so last time, right, in chapter 1, we did talk quite a bit about average rate of change. In chapter 2, we're going to be talking about instantaneous rate of change, right? How is something changing at a particular instant of time? Now that we have all of this limit information, we're really ready to tackle a problem like this. So let's think back to this example, right? The claim is I went over this back in the chapter 1 motivational video. We're driving from Lansing to Detroit. Here I have my nice graph that represents distance, right? So distance in miles away from Lansing. At what particular time is my speed the greatest, right? So this is talking about how is my distance changing, right? That's speed. Speed is how your distance is changing, feet per second, miles per hour. Again, how is a distance changing at a particular instant, right? We want to know when this is the greatest. Well, again, my speed is a rate of change for distance. And rate of change, right? We've talked about average rate of change. We're going to be talking about instantaneous rate of change. So this is really talking about some slope, right? Average rate of change was a slope of a secant line. Instantaneous rate of change was a slope of a tangent line, right? At a particular instant. So really, this is wondering when is my slope the greatest? So, right, if you want to know when the speed is the greatest, speed in this case is going to be the same thing as slope. At what particular instant is my slope the greatest? So looking at this right here, right, again, kind of before this, we always needed 2 points for slope. We're trying to get down to just 1 point with our good old tangent lines. So if I was to kind of sketch a bunch of tangent lines here, here's the slope of one tangent line, here's the slope of another tangent line, here's the slope of another tangent line, and we can see that they seem to be getting bigger, right? So the slopes of the tangent lines, you're getting more rise for your run, right? But then at a particular instant, later on, they start getting smaller, right? So actually, this is starting to mellow out. The slope is not as big anymore. So the slope's getting bigger, 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 and then it starts getting smaller, smaller, smaller. So I claim that maybe our greatest slope, and therefore our greatest speed, is somewhere around 30 minutes in, right? At time 30, I'm thinking that the slope around this point is the greatest. Again, this is an estimate because we don't have an equation, so there's not really any more math we can do, any algebra or anything like this. It's just basically staring at this graph and trying to approximate where is the slope the greatest. So again, I would say at t equals 30 minutes, the speed, which is really, again, the interpretation here is slope, right? Slope is the greatest. So again, we saw that this real-world question could be answered by thinking about slope at a particular instant. And the claim is, right, we're going to be very interested about how fast things are changing. In this case, how fast distance was changing, right? That gave us speed. You can also call this, right, velocity. But more generally, right, this instantaneous rate of change is something worth studying, right? Not just for velocity, but there's so much more. And we went over this again in chapter 1, but it's worth repeating, right? So if you wanted the rate of increase or decrease of stock values, are these increasing or decreasing, right? Because that's losing or gaining you money. Infection rates for diseases or chemical reactions, how fast are things reacting to each other? rate of population growth, rate of change of velocity itself, right? How is something accelerating? Rate of change for monthly sales at your business, rate of change for temperature, right? The rate at which a temperature changes. So all of these things are very interesting real world situations that we would like to be able to study. And the claim is with calculus, we can, and in particular with the study of derivatives. So that's why we're going to be studying derivatives in this section so that we can talk about how quantities are changing. All right, get to it in 2.1. I'll see you then.